these are pictures that I think they're taken by a famous photographer, Peter Hugo. The photo series is called Permanent Error. And it is a permanent error what is happening here. It fits into the box of Matthias, disposal and burning. The non-compliant disposal and burning. The problem with the plastics is that many of these housings, and you see especially here monitor housings of CRTs. Now the monitor housings, they contain about 70% of them contain brominated flame retardants. Now I will look at the brominated flame retardant later on because it is a myth that all of the brominated flame retardants are hazardous substances. We need to be careful there. But it is in so far 70% of these monitor housings have brominated flame retardants. And as long as these brominated flame retardants are sitting in the structure of a plastic, there's not much of a problem. Otherwise you would have a problem watching television or watching in your TV. The problem starts when you incinerate these plastics with brominated flame retardants at a too low temperature, and that's where you get furans and dioxins. So especially this practice here of burning these plastics is about the worst thing that you can do because the temperature is not high enough. This is the second part of these pictures. I can really recommend to have a look at these pictures. They are really, they're looking ugly in one way, but on the other hand, he does it in a sort of an artistic way at the same time. Peter Hugo is the name, and this series is called Permanent Error. You will find them on the internet. Now let's have a look at what I want to do. This is my agenda. So that's why I said, please fasten your seatbelts. It's a long list of things that I want to cover. And I want to start talking about the environmental aspects of plastics and what it does if we would recycle them. Now, if you look at plastics, and especially the high-tech plastics, the plastics that you typically find in your electric appliances, and that's mainly ABS and polystyrenes. These are the two main plastics that you will find, but also polypropylenes. You will find that there is very little recycled if you compare them to other commodities like glass, metals, like ferrous metals and aluminium. Very, very low percentages are recycled. Yet the value of these plastics are high. In value, if you would buy them as virgin plastics, are very high. Now, if we look at the typical way plastics are made, they're typically made from oil, as most of you probably know. They take certain fractions in the refining stages, and these fractions are then polymerized. Now, polymerization is making long chains of these fractions, and that takes up an enormous amount of energy. Right? And this is important to understand that this takes an enormous amount of energy, because by recycling these plastics, what you do is you leave this amount of energy into the plastics. Yeah? By incinerating, you take the energy again as energy, but then it's gone. So it's much better to leave these energy quantities into it. And what you need is very big plants, and what we do is we take waste. And this is a growing supply. In the past, it was typically landfilled or incinerated. Even in Europe, it wasn't very long ago that most plastics ended up in landfills. So there's nothing much strange if it happens here still. It's a self-replenishing market, and it is a growing supply. If we see how the European market, and especially the European market, due to the fact that there is legislation, has grown since 2004, it's just enormous. So there's no reason to believe that it can't be done anywhere else. Then we have a plant, and that plant is basically a mechanical mining principle. We don't do anything chemical, we simply make separations. A very complex separation, and I will get back to it later on. It's a very complex separation because one of the typical things with plastics in comparison to metals is that the physical characteristics of plastics are so near, be it density, be it color, be it, there are many things to happen. You need to do many parameters separations to get into the plastics themselves. What we do is, by separating these plastics in this mechanical way, we save about 90% of the plastics compared to the production of virgin plastics. Now, this has to do with all the energy that is put into creating these long chains. Yeah, we don't have to recreate this. We simply leave it there. And then we use the plastics again. We use much less water. And by doing so, we are saving, per ton of plastics that we produce, 1 to 3 tons of CO2. Now, I don't know if many of you are really into this concept of CO2, but what I did is I went to into the Wikipedia later on, and I will show you a little map. Now, what we do is we make green products, and even my screen is getting green. And what we call them PCR plastics. Now, PCR plastic stands for post-consumer recycled plastics. We want to make the difference between industrial regrind, which is basically taken plastics from industries and then regrinded and recreated. That's really not recycling. It's just using the rest bits and pieces, but it's not separating these plastics. Yeah? So we make the difference. We call them post-consumer recycled plastics, PCR plastics. Now this is this little map I was talking about. I live in Austria, and I think it's an easy place to explain a little bit. If we produce 3 tons of plastics, we have saved about the same quantity of CO2 emissions as the CO2 emissions of one person. And that's enormous. So there is a lot of incentive to look at the recycling of plastics, if it were only for the CO2, but also we hope to make a business case as well. Right, if we look at why we recycle, well, the thing in Europe, and I want to make a little distinction between Europe and the United States. In the United States, the company I work for comes from the United States, and we have only one small facility in the States that basically is research and development and not large-scale production. Why is that? Because in Europe there is legislation that calls for a return of these electronics and then for the recycling of these electronics. Whereas in the States, you throw it away. Yeah? The other problem in the States is that there's very funny legislation. You know, we have been talking about PCB, but now the real PCB stuff, the polychlorinated biphenyls, in the United States there is a piece of legislation that prescribes that recycling can only be done if it's proven that not more than 2 ppm of PCB is there. Now this is ridiculous. You can't even measure it. If we bring a sample to 5 laboratories, we get 5 different answers to this question. 2 PCB is not measurable. Now, if you have legislation which prescribes thresholds that cannot be measured, you cannot create an industry. And that is what is happening in the States. I get back to the same issue again when we talk about brominated flame retardants, because we have a little bit of a risk that we get into the same debate. Okay? So, legislation, thank you very much, we have legislation, thank you very much, we can do recycling. Yeah, so let's be very positive about it. Sometimes I am also a bit critical against legislation because sometimes some things are a bit squeaky. But let's face it, if we wouldn't have this legislation, we wouldn't have this amount of recycling. In our company, where we have factories in China and in Europe, both the factories in China and in Europe are fed with materials from Europe. Let's face it. Yeah? Even our factory in China gets and we use the empty containers that carry all the electronics from China to Europe, and these containers need to be returned, and what we do is we use these empty containers, fill them up with plastics, and have a very cheap transport rate to bring the stuff. You know, it's cheaper to bring material, just as a strange comparison. It's cheaper to bring material from the Netherlands to China than from the Netherlands to Austria. Logistics, by the way, and I come back to this as well, logistics is one of the most critical things for that sort of a fraction. So we can talk about plastics recycling from Nigeria, from Ghana. The most critical issue will be the logistics. Yeah, and we have to really think about it. So if we really start talking about it, logistics, let's keep it in mind. There's an enormous amount of pressure from the market, from NGOs. There is this whole concept of recycling society, whatever it may mean, but we want to move to that sort of concept, and that's in itself very good. I've just mentioned here UNIDO, I'll come back to that as well. with regards to the new POPs, a few of the brominated flame retardants have had the pleasure of being pronounced as new POPs, persistent organic chemicals, which might be an issue in the future, and I'll get back to that. But replacing virgin plastics with post-consumer recycled plastics makes sense. And I just hope that this part of the presentation has convinced you of that. So let's look at the next part of it. If you look at the amount of energy that is put into it, if you look at the amount of oil that is put into it, if we could reuse that sort of thing, but then you get very strange things. The flame retardants industry saw that televisions were phased out. Wow, we're losing a market, said the flame retardants industry. What they did, they created a new norm without the industry involving the industry very much. And they created a new norm to get flame retardants into flat screens. Now they don't create any heat. No, but you might put a candle underneath. You know, this is the sort of ridiculous things that are happening, and I'm really frustrated about that sort of thing. And of course they didn't invite the plastics recycling industry. No. The standard was there, and then the recycling industry was called in. Hey, we have to recycle these plastics. What can you do? Yeah, that's the sort of things that are happening. You know, this is economy. I hope that the market and that the reality and the normal constructive thinking of people will show that the flat screens do not need any flame retardants. But right now we have a standard in Europe that prescribes that flat screens need flame retardants. Yeah? And then we have, of course, the POP risk, which I will get back to later. Let's face it. Plastics do have compounds in them. They do have substances in them. And if we want to phase them out, we have to realize, and the legislator will have to realize, that there is a legacy and that it will take time to phase it out. You cannot expect a recycling industry to, from one day to the other, just reduce it to zero. It doesn't work. It is all to do with yields, it is all to do with separation techniques, and there is no such thing as 100% secure and precise separation. Right, a few remarks about the reality of life. If you want to use post-consumer recycled plastics, and this is particularly a remark for OEMs, these plastics are recycled plastics. We cannot make a white plastic out of a black plastic. And the majority of these things are black. Yeah? We end up, our normal standard color is gray, dark gray. Except when we recycle fridges. Then you get something creamy, you know, a little bit like that. Yeah? So if a designer wants to use post-consumer recycled plastics, don't make white appliances, for instance. Yeah? The surface may have very small defects. We can take almost everything out, but there will be small traces. So please, we have made very shiny surfaces, and we are very proud that we can do it, but it comes at a cost. You know, we need to do extra refining for it. So ideally, you would have a little bit of a textured surface, and then you can't see anything. But if you have a really glossy surface, we really need to do extra work, and then it becomes more expensive. Also, the plastics that have been used, post-consumer plastics, have a heat history. Heat history means that the length of the polymer chains do differ a little bit. In other words, you have to deal with post-consumer recycled plastics in terms of molding slightly different. You cannot simply use these plastics as if they were virgin, because they're not virgin. You know, and if they're not a virgin. So, and then with regards to the legislation, and with regards to OEMs especially, please do not make more strict rules than the legislator is already doing. That's difficult enough. You know, we are facing more and more OEMs that want to completely ban halogens. They want to completely ban all brominated flame retardants. Now, I'll give you one example. A television set has typically something like 150,000 ppm of brominated flame retardants. We can reliably bring it back to levels for REACH and even ROS. But it is more and more difficult if you really talk about 500 ppm, which we sometimes find. if you also want to take out all the flame retardants, the brominated flame retardants that still can be used. Why would you limit these things if they can still be used? That makes recycling more expensive and more difficult. There we go. That was the first chapter. Now this is a wonderful picture. This is a picture that was taken by a photographer. And you know, you'll notice I like photography, I like pictures, I like things. This is a wonderful picture made by a photographer of National Geographic. They did an article on e-waste recycling 2-3 years ago. And they came to us and we simply had this pile of unshredded plastics. And I put this picture in here not only because it's a beautiful picture. It shows two things. This picture shows that you have all sorts of appliances in here, you have all sorts of colors in here, and you also see there's a lot of air in between. Yeah. If you put a container full of this stuff, may I ask you a guess how many tons you would get into a container?
2 tons.
Yeah, 5 I think. 5 to 8, I think.
20 feet container.
20
feet container. 40 foot.
8.
Okay. 40 foot, okay.
8. Now, if you want to use and bring plastics from Europe to China, which we are doing at a rate of hundreds of containers, you don't want to ship 8 tons. You know, it's far too expensive. We want to get 24, 25 tons in the container. The only way you can do that is by shredding this material. Yeah? Shredding it into smaller pieces, and then you can easily get 24 tons in a container. You need to get to a density of about 350 kilos per cubic meter, roughly. Okay? Now, let's have a look how this works in Europe. I don't know, have you shown any pictures and films about what is happening in Europe?
Plastics.
Mm-hmm.
No.
And e-waste? Right. Now, I played around a bit. You know, this is a company in Austria, and I hope you'll be able to see it at the back, because these films are not very dense. This is what is called a smasher. Now, the smasher is basically, if you take a printer, yeah, you take a printer and you throw it on the floor, then the thing falls apart. And then you can take out the batteries, and you can take out the toner cartridges, and you can take out, yeah, that's what is being done here. So this thing turns it around, falls from 3 meters until it allows the pieces to go through holes, sieving it. And then along this line, it's a very simple machine. Along this line, you have people grabbing out the capacitors, the batteries, the toner cartridges, but also the expensive stuff, you know, the printed circuit boards. It's a very nice and neat way of dealing with depollution, right? It's a big tumbler, and then it falls apart, okay? So that's how we deal and how European companies sometimes deal with depollution. Very effective way. The next part is, of course, a shredder. Now, in this particular company, they work with a big car shredder, which they operate in batches. So they, that's true, yeah. There we go. Yeah, and in this one, they also put cars in. But, you know, they run in batches, electronics batch, fridge batch, car batch, and that sort of thing. And then, well, the fridges, we have to be careful because they need to be sorted, and only pentane fridges can go in there, and not the CFK ones. Right, and then in a shredder, a typical shredder, after the shredder you have big magnets, and they take out the ferrous, and then you have a residue, which is called, in this case, electronic shredder residue. The next step is then that you get into all sorts of non-ferrous separations. Now, all sorts of nice and clever things are happening. This is an eddy current. An eddy current is basically inducting, and some metals then get a little bit of magnetic, and they jump further away than the other ones. So you get stuff that falls like this and stuff that falls like this, and then you have a separation like this. You know, this is the basic principle. Very simple. You know, it's all, you know, Donald Duck, who reads these magazines of Donald Duck, there is this inventor, right? This, and I think that all these techniques are coming from him. This is another one. And I'm not going to show you all, but we have the time for it, so we might as well enjoy it. So this is another one. This is a density separation. A density separation is, well, easiest is water. You put stuff in water, some stuff floats, some stuff don't float. You know, a little bit like in the sea. You know, very near the sea you have the same sort of principles as well. And then you can put some media in there to make the water heavier, like salt or carbonate or, you know, what's that sort of things. And then you can do the same stuff next time. And then you can do all sorts of separations to the specific gravity of the specific density of materials. That's another technique. Yet another technique is making it very, very small, and then using what is called air tables. And then some of the stuff goes up, and some of the stuff goes down. And then you can get very, very nice concentrations of copper and even precious metal, Alexis, you'll be happy to hear. But I wouldn't propose that for plastics. That is the reason. So these are these wonderful air machines. Now that's the reason why this non-ferrous metals, where you really make them close, is not anymore in the supply chain getting to the plastics. We don't want the plastics to be too small, because we want the plastics to be in a size whereby we can do all these physical separation steps. Okay? And what we buy and what we purchase is what comes out of this system as the electronic shredder residue, of which most of the metals have been taken out. There's another concept that you will find basically in lower waged countries, like most of yours, where material is depolluted manually and where you then go through a manual dismantling system, where you typically get to these big pieces of plastic which you can't ship because they are too big. Okay? So this is what I call our supply chain. The materials that we purchase is small domestic appliances, ICT, fridges, and that's a very bad quality, I must admit, all large domestic appliances and smaller fridges. Then you can get it in all sorts of ways and forms. You know, we have people that even throw the housings in the mix, which is not a good practice. I wouldn't do this, please, because we have to go in there and manually grab this stuff out and then have them shredded. We cannot put that sort of big things in our machines. Some people prefer to bale it. I must say most of the traders like baling because they work with manual separation things and sniffing techniques which I wouldn't want to promote to anyone at all. But that's the sort of material that we typically purchase. And if you look at the composition of this material, that's what I wanted to come to, you have this pie chart, and it shows that for the small domestic appliances and ICT, about 60% is what we call target plastics. Target plastics are those that we produce. That is high impact polystyrene, it's ABS, and it's polypropylene. And then you have all sorts of contaminants. Contaminants like HIPs with flame retardants, which we need to separate. ABS with flame retardants, which we need to separate. PPO, PCABS, PC, PE, POM, PVC, rubber, wood, and also a little bit of metal. That's the typical mix that we get in our factory if you take the average over a long period of time. Now, we can perfectly live, of course, with plastics that do not have these contaminants, let's face it. You know, if you come with a manual dismantled material and that is shredded and getting smaller, you will not have any metals left, which is excellent. You know, we don't need them. Right, that is chapter 2. Still fine, Federico? No. That's what I thought, yeah? Right, legislative framework. I will do that very short, because we already discussed some of it. In Europe, the situation is fairly complex. We have a very complex legislation for the transport. As you know, it's not easy. There's a lot of interpretation, a lot of different ways of looking at the same reality. one of my tasks is to call and to discuss with many of the authorities, why does this plastic need to be 98% plastics? Why can it not? Because we take all these other things out. Notifications are nice and they're good, but they're also very cumbersome and very difficult. Yeah? And we have suppliers in countries that do not need a notification, and these suppliers often tell us, if we have to notify to deliver to you, we don't deliver. That sort of discussions are there. We have to realize that. Waste Framework Directive is there. We have the e-waste directive, end-of-life vehicles, because in the factory in England we use end-of-life vehicle plastics. Specialized factory only for plastics from cars. And then we have, of course, on the other side of our factory, so this is the entrance side of our factory. On the other side of our factory we have suddenly a product. And that product needs to comply with REACH, or if it goes back into electronics, with RoHS. And then you get into these debates that suddenly, after 2004, RoHS needs to be recasted. And then you get all sorts of politicians that believe we have to change the world by taking all the halogens out. And then you get into discussions, well, if you do that, then the whole recycling industry might come to a halt. So we have two ends where we always have big discussions, which is good, because I said already, without all this legislation, we would not have this factory. Yeah? But I want to come back to the issue of flame retardants. Flame retardants are a particular issue for e-waste plastics. They are there. Those equipments that make heat very often need to have plastics with some sort of a flame retardancy. Brominated flame retardants are very efficient in terms of flame retardancy. I just want you to be aware, there are about 65 different substances of flame retardants. Of these 65 substances, currently 15 are restricted. So I often hear talking about flame retardants, it's also hazardous and things. No, 65 substances, only 15 are restricted. Of these 15, there are a few that are really restricted. I mean, like POP, like in persistent organic pollutants. And that discussion is currently going on for Penta and for Octa BDE, which is a bit of an issue. We are talking with some authorities and some studies that are being made that want to reduce the thresholds to 100 ppm of these sort of materials. The problem with 100 ppm is that the recycling industry cannot guarantee 100 ppm, and we cannot even measure it to that extent. So that's the problem again. Currently, the threshold levels for that sort of substances is still 1000 ppm, which is perfectly fine. We can live with that. DKBDE, I don't want to even discuss it. It's a discussion, very complex discussion. It was banned in the RoHS. Then there was a debate in the European Court of Justice. There is no chemical reason to call it a really hazardous substance, but for the European Court of Justice, they didn't exempt it. So in other words, it is a restricted chemical for RoHS, and it isn't for REACH. Very strange, but that's the way of life. That's already the chapter on the legislation. I don't want to really go into RoHS into much detail. You can look at this slide. It describes a little bit. In terms of our plastics, the major important chemicals that we deal with is brominated flame retardants that we have to deal with, and cadmium. Cadmium used to be applied for coloring of plastics, orange, yellow, red, that sort of thing. Okay. The flame retardants, just a last remark on the flame retardants. Where do you find flame retardants? Now, typically, I always state, CRTs, television monitors. That's also where you can get into Octa BDE at levels that are higher than 1000 ppm. So I would be careful with monitor housings and TV housings. I would also be careful with plastics from laser printers, copying machines, and business machines that generally create heat. And these old business machines, they tend to be older than consumer electronics. Hence, the risk of them having Octa BDE is bigger than for the normal coffee making machines that you will find in households. Yeah? So generally, if you deal with small domestic appliances, household equipment, there is flame retardants, but not the pops. If you go to television sets, be careful. If you go to printers, to business machines, be careful. Generally, the industry is moving away from brominated flame retardants. If you ask my personal opinion about it, I have doubts about it, because it needs to be replaced. Flame retardancy is needed. Many people go and move from brominated flame retardants to phosphoric-based flame retardants. Phosphors are not very easy stuff. If it gets recycled, if it gets inheated, and in relation with water, can create phosphoric acid. You know, and I think that the phosphoric flame retardants might be a temporary solution, because in 10 years' time, they will be listed as restricted, is my personal conviction. So if you look at the efficiency, I think that brominated flame retardants still could be used very well, but unfortunately many OEMs decide to move away from them. Right, next chapter. I told you that I'm fairly often in China, and I just wanted to share with you what people in China do. I'm not trying to make the cause that this is the way it needs to be done. I just want to be sure that you understand this. I just wanted to share it to see how it's being done there. Much of these plastics come into China. Oh shit, what did I do? This is no, well, this is not green stuff what I'm trying to talk. Yeah, this is fine. So in China, most of that stuff, if you look at it and you ask the people where does it come from the States, it comes from Canada, it comes from Europe. That is where this stuff comes from. Right, it comes into very big concentrations. You will find big marketplaces with hundreds of tons of this stuff, you know, and all in big bags, and they're lying around and they're being transported like this. And then you get into and again, please be careful. You see that guy, he is cutting purgings without any safety measures whatsoever. Please be careful. You know, but that's the sort of way that people are dealing in China with plastics. They hand sort it, sniff very often. They bring it into some sort of a concentration of plastics, and then they do some swim think. You know, they can make the distinction between polyolefins and non-polyolefins and styrenics, and then they do some blending, you know, and then they put it through a very simple extruder. Especially with flame retardants, that's an extruder that is of some concern. But that's the way they do it. But I'm also saying, in China, you'll also find, this is a pre-processing plant for plastics in China, with all of the permits, people wearing safety things, absolutely in line with what we would consider in Europe as being doable. They do it on the basis of density sorting, washing, and then hand-picking dirt out. Yeah. That sort of pre-processing is possible, and this is the result of that sort of pre-processing. It's a shredded material, it's clean, perfectly possible to serve as a raw material for a factory like ours. Yeah. That brings me to our factories. I just want to share with you, and I want to invite you to our plant in Austria. Here is a map of the world, and you see that we have our small facility in California where it all started. And then the funny story is, when this Mike Biddle is our company founder. That's the MB. MB is Mike Biddle Associates. He started up as a consultant and then got into recycling techniques and then started up to make a factory. And one of the new shareholders of MBA in beginning of the 2000s was a company called Flextronics, a very big electronics producer. And he said, the only way you can create post-consumer recycled market is if you create a global company.